Complexity metrics are basically used to reduce the complexity of modules. Whenever we divide a large project into small modules, the real purpose is to make the project more simpler or manageable type of modules. There are several methods to check the complexity of a module before we write the program. Two methods for analyzing the complexity that we are going to discuss are Cyclomatic complexity and Halstead's measure. Let us discuss about cyclomatic complexity first. Cyclomatic complexity: identify the high complexity modules and then see whether their logic can be simplified or not. Cyclomatic complexity is perhaps the most widely used measure for complexity analysis. To understand cyclomatic complexity, first we have to learn how to represent the program by control flow graph. Simple notations for the representation of control flow graph is shown here. Each circle represents one or more source code statements. The structured constructs in flow graph form can be a sequence form or if conditional form, while form, until statement form, or case statements forms. Using these structured program construct symbols in the flow graph, we can form a flow graph. This figure maps a program flow chart into the corresponding flow graph. We assume that there is no compound conditions are contained in the decision diamonds of the flow chart. Each circle called a flow graph node represents one or more procedural statements. A sequence of process boxes and a decision diamond can map into a single node. The arrows on the flow graph called edges or links represent flow of control and are analogous to flowchart arrows. An edge must terminate at a node even if the node does not represent any procedural statements. For example, see the statement for the if-then-else construct. Areas bounded by edges and nodes are called regions. When counting regions, we include the area outside the graph as a region. When compound conditions are encountered in a procedural design, the generation of flow graph becomes slightly more complicated. A compound condition occurs when one or more Boolean operators like logical, or, and, NAND, NOR is present in a conditional statement. When a testing procedure called basis path testing method is performed, the value computed for cyclomatic complexity defines the number of independent paths in the basis set of program and provides us with an upper bound for the number of tests that must be conducted to ensure that all statements have been executed at least once. An independent path is any path through the program that introduces at least one new set of processing statements or a new condition. When stated in terms of a flow graph, an independent path must move along at least one edge that has not been traversed before the path is defined. As an example, set of independent paths for the new flow graph is illustrated here. Path 1 from 111, path 2 1, 2, 3, 4, 5, 10, 1, 11, path 3 1, 2, 3, 6, 8, 9, 10, 1, 11, path 4 1, 2, 3, 6, 7, 9, 10, 1, 11. Path 1, Path 2, Path 3 and Path 4 constitute a basis set for the flow graph in this example. That is, if tests can be designed to force execution of all these paths, that is a basis set, every statement in the program will have been guaranteed to be executed at least one time, and every condition will have been executed on its true and false sides. It should be noted that the basis set is not unique. In fact, a number of different basis sets can be derived for a given procedural design. How do we know how many paths to look for? The computation of cyclomatic complexity provides the answer. Cyclomatic complexity has a foundation in graph theory and provides us with extremely useful software metric. Complexity is computed in different ways. The number of paths here is 4, so we can say complexity is 4. Another method for cyclomatic complexity is, let V of G is the graph for the flow graph. G is defined as V of G is equal to E minus N plus 2, where E is the number of flow graph edges, N is the number of flow graph nodes. In this graph, we have 11 edges and 9 nodes. Substituting 11 minus 9 plus 2 equal to 4. So 4 is the cyclomatic complexity of this graph. Another method is V of G for the flow graph G can be defined as V of G is equal to P plus 1, where P is the number of predicate nodes contained in the flow graph G. That is, the number of decisions is 3, so complexity is equal to 3 plus 1 equal to 4. Another method of computing complexity is by considering the number of regions of the flow graph correspond to the cyclomatic complexity. The cyclomatic complexity V of G for a flow graph G can be defined as 4 by considering the regions R1, R2, R3, which are inner regions, and the outside regions altogether is taken as the region 4, and thus by considering this 4 region, the cyclomatic complexity of this flow graph can be defined as 4. So the cyclomatic complexity analysis help us to understand the logical complexity measure for testing the basis set of execution paths. Another complexity analysis is by Halstead's measure. Halstead proposed a number of measures based on his experience with software science. Some of these experiments can be considered as complexity measures. Halstead made the observation that metrics of the software should reflect the implementation or expression of algorithms in different languages, but be independent of their execution on a specific platform. In Halstead's measure, a module's connection with its environment is reflected in terms of operands and operators. So according to Halstead, length and volume is based on the number of operations and operands. Program volume is the information contents of the program is measured in mathematical bits. The length of the program is measured in terms of the total number of tokens used. Tokens are classified into operators and operands in a program. Let us count the tokens. So measurable quantities are small letter n1 is the number of distinct operators, or we can say the number of unique operators. Small letter n2 is the number of distinct operands. The number of unique operands is n2. F1j is the number of occurrence of the jth most frequent operator. Then F2j, the number of occurrences of the jth most frequent operand. Then the vocabulary of the program n is equal to n1 plus n2. The total occurrences of different operators in the program capital N1 is equal to sigma F1j, and the total occurrences of different operands in the program capital N1 N2 capital N2 is equal to sigma F2j. Then the length of the program n is equal to n1 plus n2, which is different from Halstead program length. Halstead program length h is equal to n1 into log n1 base 2 plus n2 into log n2 base 2. Volume of the program v is equal to n log n base 2, which represents the minimum number of bits necessary to represent the program. These equations are highly correlated with the size of the program LOC. I know that LOC is the common measure which is selected for the size measurements. So the different measures can be represented with these different formulas: program length, program vocabulary, volume, effort, and Halstead program length can be identified using the number of operands and number of operators with these various formulas. Now, to understand more clearly, let us consider an example. Consider this following C program: main int a b c avg scan percentage d ampersand a ampersand b ampersand c average is equal to a plus b plus c division 3, print average. So in this program, the unique operators are main, bracket, curly brace, integer, scanf, ampersand, equal to, plus, slash, printf, double quotes, semicolon. That is, we have 12 operators, n1 equal to 12. Unique operands are a, b, c, avg, percentage d, 3, avg equal to percentage d. That is 7 unique operands. So n2 is equal to 7. So small n1 plus small n2, 12 plus 7 is equal to n is equal to 19. Now we are considering the total occurrences of different operators in the program. N1 is equal to sigma Fij. The value is 27. Similarly, we are calculating the total occurrences of different operands in the program. N2 is equal to sigma F2j, which is equal to 15. So capital N is equal to N1, capital N1 plus capital N2 is equal to 42. Now substituting these values, Halstead program length H is represented here as n cap is equal to n1 into log n1 plus n2 into log n2 equal to 12 into log 12 base 2 plus 7 into log 7 base 2, which is equal to 62.67. Now program volume, the information content is calculated as the program length times the 2 base logarithm of the vocabulary size, that is V is equal to capital N into log small n base 2, that is volume is equal to 42 into log 19 base 2 equal to 178.4. Now calculating the difficulty level or error proneness of a program is proportional to the number of unique operators in the program. Difficulty level can be calculated as small n1 by 2 into capital N2 by small n2. Substituting D is equal to 12 by 2 into 15 by 7 equal to 12.85. Now effort can be calculated by multiplying the volume with its difficulty. So substituting the value of difficulty and volume, 12.85 into 178.4 equal to 2292.44. In Halstead's measure, a module's connection with its environment is reflected in terms of operands and operators. A call to another module is considered as an operator, and all parameters are considered operands of this operator.